Jai Hind, my name is Vaishali Deshwal and I am currently working as an assistant professor at AKGEC. So today is the second lecture of machine learning techniques and the code for this subject is KAI 601. So we'll continue from the last lecture. So in the first lecture we have discussed the different types of machine learning techniques like supervised, unsupervised, then in supervised we have discussed the two categories, in unsupervised we have discussed two categories, and last time we were discussing reinforcement learning. So we'll continue from that slide only. So in reinforcement learning, we have been discussing the real world use cases of reinforcement learning. So, or you can say the applications of reinforcement learning. So first is video games. That the RL or reinforcement learning, they are much popular in gaming applications. It is used to gain superhuman performances. For example, AlphaGo, AlphaGo Zero. So these are some of the popular games that use these algorithms, RL algorithms. Then second application is resource management. So resource management with deep reinforcement learning. So this is a paper, you can say, reinforcement management of deep reinforcement learning paper. This is a paper and it shows that how to use reinforcement learning in computer to automatically learn and schedule the resources to wait for different kind of jobs. Third thing is robotics. So robotics is widely being used in robotics applications. These are kind of the application they have different applications in robotics. So robots, they are used in the industrial and the manufacturing area, and these robots, they are made more powerful with reinforcement learning. So there are different industries that have their vision of building the intelligent robots, and for these industries the RL algorithms, they are quite useful. Then next application is text mining. So text mining is the another important application of this reinforcement learning, or you can see the application of the natural language processing. So is now being implemented with the help of reinforcement learning. Next topic is well-defined learning problems. In this, we'll see that how can we say that whether a learning problem is well-defined or not. So first thing, in a learning problem to identify, we need to identify in a learning problem that whether we are able to identify three things: T, P, E. T is task, P is performance, and E is experience. So if we are able to identify these three things, then that particular learning algorithm is the well-defined learning problem. So a computer program is set to learn from experience E with respect to the sum class of task T and performance measure P. So if its performance at task in T as measured by P improves with experience E. Next is that in general, to have a well-defined learning problem, we must identify these three features. First is the task of the class of task, then the measure of the performance, that how to measure the performance which has to be improved with the time or with experiences, and what will be the source of the experience, whether it will be a database or different kind of the experiences. So for the well-defined learning problem, we need to identify these three features or the factors T, P, and E. For example, a checkers learning problem. So in checkers learning problem, the task is playing checkers. Performance measure is the percentage of, or you can say the percent of games won against the opponent, and the training is training experience is playing practice games against itself, the agent playing practice games against itself. So there are three features. We need to identify these three features in order to make a learning problem a well-defined learning problem. Then the next example is of a handwriting recognition learning problems. So in this, the task can be recognizing and classifying the handwritten words. Second is the performance measure, that is represented by P, and it is the percent of words correctly classified. And the last is E. E is the database of handwritten words with the given classifications. Next, we have a robot driving learning problem. So these are the three examples. You can find these examples in a book written by Tom Mitchell. So the third example is the robot driving learning problem. You need to identify the three things, T, P, and E. So what is a task? Task is driving on a public 4-lane highways using vision sensors. Then the performance measure, P, it can be average distance traveled before an error as judged by a human overseer. So, and then next is E, that is the training experience. So the training experience could be a sequence of images or the steering commands recorded while observing a human driver. So this can be the experience, or it can be a source of experience. So these are the three examples that how can we have a well-defined learning problem. So there are three things, T, P, and E. Next we have designing a learning system. So how to design a learning system? To get a successful learning system, it should be designed. So for a proper design, several steps they should be followed, and several steps means for perfect and efficient system, there should be a procedure, there should be some step which needs to be followed, so that in the final step we get a learning system design. So in order to have a successful learning system, it is must to design it, or for that we should follow a procedure. So there are 4 steps, and after that we will have a final design. So first thing is choosing a training experience. Second point, or the second step, is choosing the target function. Third is choosing a representation for target function, and fourth is choosing a learning algorithm for approximating the target function. And finally, after following all these steps, we'll get final design. So let's discuss these step one by one. First is choosing a training experience. So how to choose a training experience? So in choosing a training experience, 3 attributes are taken. First is the type of feedback. There can be 2 types of feedback. It can be direct or it can be indirect. So while choosing the training experience, 3 attributes or the 3 factors, they are taken into consideration. First is the type of feedback, second is degree, and third is the distribution of examples. So first is type of feedback. It can be direct, it can be indirect, and the degree and the distribution of examples. So let's discuss these things or these factors. First is the type of feedback. So type of feedback is that whether the training experience provide direct or indirect feedback regarding the choices made by the performance system. So the feedback can be direct or indirect. For example, checkers games and the learning driving. So if you are getting the feedback simultaneously or at that time only, then that can be direct. Okay, so it can be of 2 types. Second is the degree. Degree means degree to which the learner will get control the sequence of the training. Means to what degree or to what extent a learner will control the sequence of training. For example, learning driving. So learning driving, it can be accomplished in 3 modes. First is with the trainer's help, second is with trainer's partial help, and third is completely on your own. So it means, or it is showing that to what extent a particular trainer or the learner has the hold of its own actions, can able to control the sequence of training. So if we see the first mode, that with trainer's help, then there is no control. In second, the learner will have some control over the sequence, and in third one, completely on your own, means you know how to drive, but still you are having a trainer with you. But in this case, you will have a control or high control on the sequences of training. Next point is third point is distribution of examples. So in distribution of examples, it says that how well it represents the distribution of example over which the performance of final system is measured. So in this, the more possible combinations, then more situations, more examples, learning over distributed range of examples, means that different kind of the examples can be taken. The learning can happen over the distributed range of example, and we can create or we can train the particular model in the different kind of situations. For example, if the task is learning driving, so it can be happen in two modes, with the trainer, without trainer, and with the trainer also in a single lane, or the situation can be 4 lane, or it can be a street, or it can be in the hilly areas with trainer, without trainer. So there can be different kind of the situations, and if there are more situations, then there will be more examples. So the third point is all about that how to represent the distribution of examples over which the performance of the finance system is measured. Next step is step 2, that in this we have to choose the target function. So how to choose the target function? So it represents that what kind of the knowledge is learned and how it is used by the performance systems. Now in this we are taking an example of checkers game. In checkers game, so suppose there are certain rules to play checkers, and I will be discussing some basic rules here. So in checkers game, suppose this is the board, and we have some rows in the columns. So there are some rules of the checker games. First is that travel only in the forward direction. We have to move only in the forward direction, first thing. Second, only one move per chance, means the agent has to move only once per chance. Then it can be only in the diagonal direction, it cannot be left or right, it can be only in the diagonal direction. As you can see here, so if the agent is here, then it can move diagonally only. And fourth rule is that jump over the opponent. The agent, suppose there are the two players, player 1 and player 2. So player 1 can jump over the opponent or the player 2. So here we have taken some notations. First is the target function. So target function is represented here as VB. So here V is small v is the board state in which the agent is present at present, and the legal move set is represented by capital B. So capital B is representing the legal move set or the set of the legal moves, and the board state is represented by small b. Now there can be different values for this VB. So define the target value for the board state B in B, means this is the capital B and it represents the set of the target values, the set of the legal move set. So this is B, and there are number of the board state in that is represented by small b in the capital B. There can be many. So for these small b, you can say the board state B, we need to define that what will be the target value, that is VB. So if the B is the final board state, so understand it that if we have the different values for the board state, then there will be the different values for the VB also. So here are the four values of VB on the basis of the different values of small b. So if the B or the board state value is if the board state is the final board state that is won, so the VB value is 100. Second condition is that if B is the final state and that is lost, then VB is minus 100. Third is that if the B is a final board state that is drawn, then VB is the 0. If it is won, then VB is 100. If it is lost, then VB is minus 100. If it is drawn, then it is 0. Means the player 1 or the player 2, and player 1 doesn't won and player 2 also. Then fourth is, if B is not a final state in the checkers in game, then VB is equal to VB dash. Suppose here, I'm saying that suppose the agent is here, and if it is moving in the second box, then third box diagonally, and if it is not reaching in the final state, it is in suppose it is here somewhere in the middle, so we can say that VB is equal to VB dash. B dash is the best final board where the agent can reach, that can be achieved starting from the B. So here the value of the VB is VB dash only. Okay, so step third is that how to choose a representation for target function. Now we have just defined that what is the target function, that is the VB. We have already see that what can be the values of the VB on the basis of the small b. Small b is the board state. And now in the third step, we have to choose the representation for the target function. So for any board state, we just calculate the function C as a linear combination of the following board features. So it can be represented as CV. It can be represented as CV. So here are the features, that is the x1, x2, x3, x4, x5, x6, and x1 means number of the black pieces on the board, x2 number of the red pieces on board, and so on. Suppose x6 represent the number of red pieces threatened by black. Now we have to represent the target function. There should be a representation of the target function. So as you can see here that V cap B, it can be represented as this. So W0 plus W0 plus W1 x1 plus W2 x2 and so on up to W6 x3 x6. So here x6 is the feature, is one of the feature. W is the weight, or you can say the numerical coefficient or the weight of each feature, and it simply gives you the value, or it determines the weightage and the importance of a particular feature. That if this feature x5 is more important in comparison to x6, then I will assign more weight to x5. So weights are nothing, they are the coefficients which determine the importance of the particular feature. Okay. Next we have step 4. So in step 4, we are just choosing a learning algorithm for approximating the target function. That how to choose a learning algorithm. So to learn a target function, we need a set of the training examples. Means we describe a particular board state B and the training value, that is V train B. So we have to define two things, the board state B and V train B. We have to define two things. So here the ordered pair can be B and V train B. It means board state and the training value. So the training example representation, it means that a training example, it can be represented as the ordered pair. In this ordered pair, we have board state and training value. Then again, we are taking an example here. Suppose this is the example. We are saying black won the game. So if black won the game, it means x2 is equal to 0. Why? Because x2 represents the number of red pieces on board. So black won the game means there is no red, so which means x2 is equal to 0 and V train B is plus 100. It represent 100 represent, this is 100, so it represent if B is the final board state, that is won. So for the winning state, we are just adding plus 100, and here if we are considering black won the game, then we are saying this thing, that in x2, that is the number of red pieces on the board, they are 0. If it is 0, we are just giving the values to these features, that x1 is equal to 3, x2 is equal to 0, x3 is equal to 1, x2 is 0, x4 will be 0, x5 will be 0, and x6 will be 0. Why? Because there is no red. For example, x6 is equal to 0. So we'll see this number of red pieces threatened by black. So if there is no red piece, then the value of x6 will be 0. So here we can just write these features and the values and plus 100 in this way. We need to do two steps in this phase. First is the estimating the training values, and second is adjusting the weights, that we have to assign some values to the weight. So in the first step, that in which we have to estimate the training values. So in every step we consider the successor depending on the next step of the opponent. So in this with this equation, like V train B and V cap successor B, it represents the next board state. So it estimates that this move will help or destroy the opponent. So it represents the approximation. V cap represents the approximation. So in this way we can estimate the training value, that what would be the next step. Then secondly, we have to adjust the weights. So there are some algorithms to find out the weights of the linear functions, and here we are using this particular algorithm, that is LMS. LMS is the least mean square. So least mean square is used to minimize the error In error, we have this particular formula that V train B minus V approximation B cap 2 or power 2, you can say. So if error is equal to 0, then we do not need to change weights. If error is positive, then the weights is increased in proportion. And if error is negative, then the weights is decreased in proportion. So this is a concept of LMS algorithm, which is used to adjust the weights. There are a number of algorithms to adjust the weight, but in this, for the linear functions, to find out the weights of the linear functions, we are just using this thing, that is the LMS. And finally, we are having the final design. So in final design, we are having 4 components. First is performance system, critic, generalizer, and lastly, we have the experiment generator. So we are having 4 modules here. So the flow is like this. First thing is performance system. In this, it will take the new problem as input and it will give some of the solution traces. So the input will be the new problem and the output will be the solution traces. For example, the game history and any kind of the data. Then solution trace will be given as an input to critic component or the critic module, and then it will give the output training examples as output. Then training example will serve as an input for generalizer, and generalizer will generate a hypothesis, that is the output. It can be true, it can be false. So generalizer will generate the hypothesis. Then hypothesis serves as an input to experiment generator. This is a fourth module in this final design, and again we'll have a new problem. So this step is repeated until and unless we have the improved problems. Like in order to remove or improve the problems, we perform these steps: first, second, third, fourth: performance system, critic, generalizer, and the experiment generator. Finally, in the third step, we have the hypothesis. It can be true, it can be false, and it will serve as an input for the experiment generator. And again, this step is repeated in order to improve the further discrepancies or the errors, you can say. So this is it for today. We have completed the reinforcement learning, the application of reinforcement learning. We have already seen several examples of the well-defined learning problems, whether it can be handwritten or handwriting problem, or it can be anything. You need to just identify the 3 things, that is TPE. T is the training, P is performance, and E is the experience. And finally, we are having this designing a learning problem. So there are 4 steps, and finally we are having this final design. So this is it for today, and in the next lecture we'll discuss the next topic. Thank you.